So I want to spend a few minutes talking about computing derivatives and computing antiderivatives. Let's go back and look at derivatives to start with. There are a number of derivative rules that we learned at the very beginning. We know the derivative power rule, we know how to take the derivative of an exponential function or a logarithm, we know how to take the derivative of sine and cosine. Through that, we worked out how to compute the derivative of other trigonometric functions. But there are three very important derivative rules that I want to talk about. The product rule, the quotient rule, and the chain rule. We use the product rule to take the derivative of a function that's assembled via product, the quotient rule to take the derivative of a function which is assembled via division, and of course the chain rule to take the derivative of a function assembled via composition. So if I gave you something like f of x equals sine of, let's say, x squared plus 3 times e to the x all over x plus 1 to the 50th, you could eventually take the derivative of that. You would need the chain rule to take the derivative of this part. You'd need the product rule to take the derivative of the top because it's assembled via product, all this times that. And you need the quotient rule to take the derivative of the top divided by the bottom. You could take the derivative of that. It would just take a little while. You'd need to apply the chain rule twice, the product rule once, the quotient rule once. But if we look at antiderivatives, we don't have an analog for one. There's no antiderivative product rule, although in some sense there's a limited version of this, which you'll learn about next semester. There's no antiderivative quotient rule, and there's no antiderivative chain rule. So in terms of taking a function that's assembled via simpler functions using these very common connections of multiplication, division, and composition, we have no analogs in terms of taking antiderivatives. So we have no go-to tools for computing antiderivatives. Therefore, when we really get into taking antiderivatives, as I said, the U substitution is the first really interesting antiderivative pattern that we'll study. For those of you moving on to Calculus 2, you will learn a great many more, but they're not like the product rule, quotient rule, and chain rule for derivatives, where they work in all cases where you use products and quotients and compositions. It's more like if you see something like this, try that. If you see something like this, try that. And so I always say that taking antiderivatives is a bit more of an art versus a science for taking derivatives. But what's even worse, better, more interesting, depends on how you look at it, is there are plenty of antiderivatives which can't be written down in terms of any function you would recognize. Here's one. E to the x squared dx. If I put an x right here, we did that problem in the previous video. We know exactly what to do. We would just use U substitution. But if there's no x here, if we just have e to the x squared dx, then not only do we not know a technique to be able to compute the antiderivative, it is impossible to write this antiderivative in a finite way using functions you would recognize. That can be proven. That's actually old mathematics. It's amazing to show that you can't do something. So this isn't a comment on the state of our personal ignorance, that we don't know the tool. It's not a comment on the state of the current ignorance of humanity. We can prove that it is impossible to write down the antiderivative of e to the x squared in a finite way in terms of functions we would recognize. Functions like sine and cosine and power functions and exponential functions and logarithmic functions and sums and products and quotients of all those things. It just can't be done. And so this very important function, this is related to something that some of you from a statistics class may have seen before. We just cannot go and write down its antiderivative, even though the antiderivative itself is a perfectly nice function in the sense that it's a very nice curve. But we can't go ahead and write it down. So taking antiderivatives is not, in a sense, at all like taking derivatives.